there's gonna be no new algorithm today, but we're gonna see like a lot of new notions. Okay. Basically, what we're gonna do is to extend what we have seen, a bunch of notions for expanders to directed graph. Okay. So I hope that from this class you will absorb this new notion, and then after that we're gonna exploit it. Yeah.
So just one thing, are these related to what we learned in the previous class about work one, I mean, like what are the macro approximation algorithm what we have?
Yeah. So this will not be like it will not use approximate max flow as a black box. Like we just gonna build up kind of what's the notion of expanded decomposition, what is expanded hierarchy in directed graph. We build this up so that we can get exact max flow algorithm later. Yeah. Okay. So yeah. So today you can think like it's as if we can forget about like 10 previous class. But yeah, just kind of go back to basics, like existential proof, no algorithm today. Okay. But after that, just tomorrow already, we're gonna come back to push the level. Yeah. Okay. So first, let me just talk about recall some basic notion in directed graph, right? Okay, we're gonna from today onwards, we're just gonna exclusively focus on directed graph. Okay. And okay, we all know what is directed graph, but let me just recall that a DAG, a directed acyclic graph, is just a graph without cycle. Directed graph without cycle, like this is for example. And for any DAGs, you can get the topological ordering like this. Okay. So this is just basic thing. Okay. And also we can talk, like there is the notion of strongly connected components or strongly connected graph. So we said that the graph G is strongly connected, right? If the following is true, for every pair of nodes, okay, there are paths from both U to V and V to U. Okay. So for every pair, you can go and come back. Okay. So for example, this is strongly connected, but this is not because A here cannot come back to B. Okay. And we also know that every graph can be partitioned into strongly connected components, which is just like parts where for each part here, right? Every pair here are strongly connected. As in like there are paths that kind of, they all can reach each other like a back and forth. They have round trip path. This two and this two. And sometimes instead of saying strongly connected components as a word, I sometimes just call it strong component or just component, just for short. Yeah. So, okay. So you think of strongly connected component as an analogous notion as connected component in undirected graph, but here we need to talk about like connection in two ways. And the useful way to think about any directed graph actually is this, which is you should think like every directed graph is a DAG of strongly connected components. This is the way that you should imagine what directed graph is. And directed graph is like collection of connected components, disjoint connection of components. But directed graph is a DAG of strong components. Okay. Have you seen this before? Just wondering. You have seen it before, right? Okay, so yeah. Good. And next is just the notion of cuts. This is just for notation. Let's say that the graph is directed and you have edge capacity. Then if you look at any set S here, we can talk about out cut and in cut. Okay. So the size of out cuts is just the number of edges going out or the total capacity of edges going out. So in this case, out cut size is 3 if edges has unit capacity. And the in cut size here is just the total capacity that of edges coming to S. This is 5. Okay. Okay, so that's the basic thing. Right. And now we're just gonna now talk about expansion in the related graph. Okay, what is cut expansion? So previously, we said that a graph is cut expanding if there is no sparse cut. And here it's going to be the same, like similar. Okay, so but now like the cut has direction, like there are in edges and out edges. So I just need to talk about whether the cut is out sparse or in sparse. So we said that this cut S is out sparse if naturally the out cut size is small compared to the node weighting on like this is S is out sparse with respect to A if the out cut size is at most 5 times the node weighting on the A side and the node weighting on the other side. Okay, sorry. Node weighting on the S side and node weighting on the other side of S. Basically, if you have a cut and the number of in edges can be huge, but the out guy is small compared to the volume here, then that's out sparse. And in sparse is justified analogously. And sometimes when I say a sparse cut, I just mean it's either out sparse or in sparse. It's just sparse in some direction.
So if we have if S is an out sparse cut, doesn't that make V minus S in sparse too? Or
yeah. If S is out sparse, then V minus S is going to be in sparse. Yeah. Okay. Just some example so that you really get the idea. Like if G is not strongly connected, then you actually know that there must exist a zero sparse cut. Why? Because if it's not strongly connected, you know that there must exist some cut, right? Like there are like two separate strong component. So there is just one edges only in one direction crossing this cut. So in this case, this is going to be 0 in sparse, and this is going to be 0 out sparse. Okay, so now we can say what is expansion, cut expansion. Cut expansion is just, we said that the node weighting A is cut expanding, phi cut expanding if there is no phi sparse cut out or in. Okay. So what does it mean? It means that when you look at a graph, let's say if A, let's say this is a graph, and if A is expanding, this is A, is expanding. It means that when you take any cut, then it should have both a lot of out edges and in edges compared to A. Okay. So that's what it means to be expanding in the related graph. It's like a lot of edges in both directions crossing the cut. That's the, okay. So many edges on both sides. That's the keywords. Okay, so that's cut expansion. Questions about this notion? Okay, so now let's talk about flow expansion. Okay. To talk about flow expansion, we need to talk about flow and demands. Okay. So, okay, again, a multi-commodity flow, or F, assign flow value on path. But here the graph is directed, so it's assign flow value on directed path. For example, like this is like one path here, this is another path here, one path here, another path here. Okay. Okay. And now we can talk about demand. And so far in our class, when we talk about demand, we usually just talk about symmetric demand. And today, I would just want to stress that we really talk about symmetric demand today. Like, okay, the demand is symmetric. So it's assigned some value to each unordered pair of vertices. So today, we talk about symmetric demand. And we say, naturally says that the flow routes this demand D. Well, if for every pair, the total flow value from A to B is the demand between A and B. And also, another direction is true as well. The total flow value from B to A as well is equals the value of the demand from between A and B. So if the demand are asymmetric, like you don't need this for both directions, but today, demand is symmetric. For example, this is an example that when the demand is between A and B, demand between A and B is 1, like here, and demand between D and F is 1. Okay. Then this flow, the flow that consists of blue path and purple path, this flow route this demand. So you need flow on both directions from A to B and B to A, from D to F and F to D. Okay. Then we said that this flow route this demand. Okay. Good. And okay, flow expansion. We said that the vertex node weighting is flow expanding in G. If for every demand, every symmetric demand that respect phi A is routable in G. Or in other words, for all A respecting demand, symmetric demand, D is routable in G with congestion 1/5. So it's just the same notion, except that I insist on like only trying to route symmetric demand. Okay. Questions?
So congestion is still the same definition.
Congestion is the same definition. Yeah. Like if there is some directed edge there are like a lot of flow paths crossing this thing, you just kind of look at the total flow crossing this edge divided by the capacity of this edge. That's the congestion on that edge. And the congestion of the flow is just maximum congestion over all edges, like that, just like before. Okay, so you might ask, okay, why are we insisting in only talking about symmetric notion? Right, because here, like both notions are symmetric. Here, like when A is cut expanding, I need that there is no out or in sparse cut, both direction. For flow expanding, I try to send flow only for symmetric demand. Okay. So this today notion is symmetric. And why is that? Why do we want to talk about this? Well, okay. One reason is actually like okay, it already generalized the notion in the notion that we learned in the undirected graph. Okay? So when the graph is undirected, these notions already like kind of just specialized to cut expansion and flow expansion that we learned, the notion that we have learned about. So it's already like a nice generalization. Okay.
Thank you.
But the more important reason is this. The reason is that you can show flow cut gap, polylog flow cut gap. So in the what's the point? Okay, I just want to recall when we learned about flow cut gap, right? Basically, we say that like the two notions of cut expansion and flow expansion are basically the same up to log factors. Okay. So what was the point there? Like the point is that flow expansion is the notion that you can like model it as a LP, as a linear program, so that there exists some polynomial time algorithm to check flow expansion. And if cut expansion and flow expansion are kind of the same, then it means that you can approximate cut expansion. So to bound flow cut gap here, it was really basically the starting point that we can hope for polynomial time algorithm. That was the starting point, and throughout the course, we basically tried to make it fast using cut machine game and so on. But without this, you cannot really hope for fast algorithm with polylog approximation ratio. Like you see, like all the objects that we talk about, like tree flow specifier and anything, like the quality is like polylog. Okay? The reason that we have this, you have flow cut gap as basically the starting point. So now, for this symmetric notion of flow and cut expansion in the rigid graph, the flow cut gap is at most log square. Okay? We can show this, but I will not show it to you, but like the proof actually is similar. Okay. It's not as good as the undirected case when the gap is just log n. Here is like at most log square. I'm not sure if we already know that you can get n log n yet. This might be known, but what I know is that we don't know log n. Okay. It's not tight yet. So what do I mean here specifically? I mean like if A is flow expanding, then A is cut expanding. Flow is stronger. And if A is cut expanding, then A is also phi over log square. It's cut expanding. So we lose some polylog factor, but they are kind of the same. Okay. And once we have this, then we can basically like we can get like at least now polynomial time algorithm to approximate cut expansion, and also like we're gonna see like roughly how to like basically the cut matching game that we learned about can be generalized to the rigid graph under this notion.
So we also don't know if like it can go lower than that either. Like,
No.
it could be log n, or we know that it isn't.
It can be log n. We don't know.
Yeah.
It cannot be better than log n because the gap is already there for undirected graph. Yeah. So, yeah. Now, it turns out that for a natural notion of asymmetric notion, like we can talk about like some notion of asymmetric flow expansion, where instead of insisting on only routing symmetric demand, you can route any demand, like the demand from A to B and B to A don't need to be the same. One can try to define that, but for some natural notion, you can actually get the gap which is as big as n to the 1/7. It's not polylog anymore. And once that's the case, that is kind of the barrier for this notion to lead to like polylog things. Okay? Polylog quality objects. Okay. So that's basically the key reason, okay? Because of this barrier. Okay. We will not see this, but we will not see this gap. But if you want, you can have a look. And actually, Gary here is like the expert in this subject actually. Okay. So let me just mention one open problem, some open problem. The concrete problem is like to close the gap for the symmetric case. It has been there like for a long time. I'm not sure if, again, I'm not sure, maybe this is already n log n, but the gap is there. It's a really important gap. And close the gap for the asymmetric notion, the gap there is kind of big too. Gary, this is the best known gap right now, right? Or it's already improved?
I think the asymmetric upper bound is like a little bit smaller than.
Okay. What's the known upper bound?
It's like some weird fraction, like 1/2 minus epsilon or something.
Okay. Interesting. Something here. Okay. Okay. Good. So this gap is like considered really important to try to close. But one non-concrete problem is actually like I hope that like one can hope to define some asymmetric notion of expansion such that you don't suffer from this polynomial barrier. Okay. Can we hope for some natural enough notion that it still can lead you to some polylog approximation algorithms? That's a really interesting question. But anyway, today we talk about this cut and flow expansion in the asymmetric way. Okay. Now I can talk about expanders. What's expanders? Well, just like before, I just said that the directed graph is a phi expander if the node weighting is phi expanding. Can be cut expanding or flow expanding. This is just the same. And I'm gonna use this convention again that when a graph has more than one strong connected components, when there are more than one strong components, it means that like there are like this kind of cuts, right? That is like a zero sparse. Okay. So like they are kind of separate components anyway. But I just gonna use this convention to say that A is phi expanding in G if it's expanding in each component. That is, for each component U, A intersect U is phi expanding in G. For example, look at this graph. Okay. This is like a components, and they are like these are separate components, right? Because you can only reach each other only in one direction, not two directions. These are separate components. And I'm going to say that A is expanding if, when you look at each component here, A is expanding here, A is expanding inside here, and here. Just like before. Okay. So G is phi expander if every component of G is phi expander. Okay, so now let's see example. Okay. So you might recall this quiz that we talk about in the undirected setting. Okay, and we see that like this part is expander. This is expanded too. This is not. So let's do something similar today. Okay, and tell me which one is expander. Okay. So let's start with a click. A click where like you really have both edge in both directions. Okay, for every pair of nodes. Is this expander? Yes, right? How about single vertex? Yes? Okay. How about star, where you have like both direction? This is the case too, right? This is less obvious, but yeah, like you can actually like, you can see that there is no sparse cut basically. Okay? Because look at any cut, if it contains 3 leaves, you're gonna have like edges in both sides, like 3. Okay? What about the star on one direction? Is this an expander? Why? Yeah.
Or go ahead. All the strongly connected components are just like singletons.
Exactly. Each strong component are just singleton.
So would it be kind of similar to the DAG of expanders? I
Yeah.
guess? But every component is just a single vertex.
Right. Okay. Yeah. So in general, if it's DAG of expander, this is expander. Right? And in particular, just a DAG is expanded in the sense that like each component is expanding because each component has one node.
I mean,
This-
so the single vertex is an expander, so
Exactly.
because of that, everything else
Exactly. Yeah. Empty graph
it is.
is expander. 2 clicks is expander. What about this one? Clicks, and you have connection here.
Would the thing connecting them be a sparse cut?
Yeah,
So it's not an expander?
exactly. Like, because you see that this is one strong component. This whole thing is one strong component. And this cut is sparse. On the other hand, if you look at this one, is this expander? This is expander now because actually like they are not in the same component. So this cut, you don't need to like we don't consider it. We only look at like each component here, and this one like each component itself is a expander.
Yeah, it would fall under the DAG again.
Yeah. This is just a special case of DAG of expander. Okay. So bidirectional path, is it expander? Why? Yeah.
We can just take the edge on the like in the middle of the path.
In the middle.
Should be like root and node weighting on each side,
Yeah.
and you only have like one in edge and one out edge across.
Yeah. Like if this is of length n, just take the cut in the middle. This is bidirectional, so like this whole thing is one strong component. This cut is a cut that separates volume of n using a cut of size 1. It's a sparse cut.
Wouldn't like if we had a similar thing that's just like a directed cycle, that would be like a similar argument where you just cut 2 edges and then you have the same node weighting.
Yeah, if it's the directed cycle, good. Then there is a sparse cut. Yeah. How? Like you can maybe like cut one edge here or cut one edge here. That would separate the things. But if the path is directed, Now this is expander again. Okay, questions about this? Yeah. So this is like, all these are expanders. This is expander, this is not. Okay. Good. And this one, this is just from before, right? Like if we can talk about expanding node weighting. And if this is a clique and like some node weighting is inside the clique, then this is expanding, although the whole graph is not expander. Okay. This one, is it expanding? This set of edges here? Yeah.
No, because again we have the bidirectional edge, so they're in the same component.
This is sparse cut with respect to f. Because just cut one and it separates a lot of f from each other. And again, this one is expanding because they are not in the same component anyway. Okay. Questions? Okay, so I hope you get some like an intuition about directed expanders, okay?
So, in a sense, a bidirectional graph works very similar to an undirected graph.
Exactly. When each edge is bidirection, everything is just the same as before.
Okay.
Just the same, exactly the same. But now, edge can have direction, and that's we try to generalize it today. Yeah. Okay, so now that we know what is expanders, okay, I just want to mention, like, you can call it a paradigm, how to design algorithm, okay. Expander paradigm.
I have a question.
Yeah.
Suppose we have a bidirectional graph.
Yeah.
But, I mean, the node weighting is different in each direction. So the edge weighting is different in each direction, for example.
Edge weight. No, sorry. What do you mean?
Sorry, like, let's say you have like from A to B, the flow, the weight is like, let's say 5, and in the opposite direction it's 10.
You mean the cut?
Yes.
A and B, and this direction is 5, and another direction is 10.
Yeah.
Okay.
In this case, would it still like, so so will that, will you be taking the flow, like the overall flow and say, okay, because the direction is 10 in the opposite direction, the net flow would just be 5, or how exactly would be?
Oh, so if the axis is cut, right, then any symmetric demand that sent across this can be of total demand of 5 at most.
Okay.
Because if I want to send 10, okay, in this direction I can send, but then there is a bottleneck here.
Okay.
And the demand is symmetric. So I need to send in both directions.
Okay.
Okay. So, expanded paradigm as a how to design algorithm. Okay, you have learned dynamic programming, divide and conquer, that kind of paradigm. You can think of what we have learned in this class as kind of specialized notion of like some algorithmic paradigm too. What is that? From what we have seen so far in undirected graph, we cannot follow this template. We just start with whatever graph problem we want to solve. Just try to solve it on expander first, on connected, like just one connected component of expanders. And then you just try to make it work in any graph. How? Just apply expanded decomposition separator expanding hierarchy or boundary separator expanding hierarchy, SE or BSE hierarchy. Let's see some example. We see edge specifier. If you don't remember, recall this. Yeah. And we just see like a simple algorithm on expander just by simple random sampling. And we generalize to any graph using repeated expanded decomposition. We see connectivity oracle, and we first show how to do it in expander, and then using SE hierarchy just works in any graph. And just most recently, like this approximate max flow, we see how to do it on expanders. And just last Friday, we see that, okay, using BSE hierarchy, which implies tree-flow specifier, you can just make it work in any graph. So this is like a template that have been quite successful in like the last 10 years. Can we have something like this in the Redis graph? That's the question. And it turns out that maybe in the like a last 5 years or even less, it seems that there is this emerging paradigm, which is like this. It turns out you need to start designing algorithm from two special cases. One case is the same. Start from just one connected component of expander. And another case, which is kind of extremely opposite of expander, is just a DAG. Right? The DAG is kind of opposite of expander because you see like it's just a graph that are full of zero sparse cut. It's very not expander, but it's still non-trivial. This is the DAG. So design algorithm on the DAG, design algorithm on expanders, on connected expander. And then it turns out that when you have both, then you can make it work in any graph. How again? Just use the same kind of thing that we have learned when you lift it to the derived case. Okay. So this is what we're gonna I can tell you what is this thing today. Okay. What is expanded decomposition and expanded hierarchy in the Redis graph?
So this is essentially what we're doing when we like apply this expanded decomposition or whatever like hierarchy we're picking. Then that kind of gives us this like a bunch of expanding components, and then we have like in some sense like are combining them through the algorithm on the DAG.
Yeah.
Like stitch it together.
Yeah, that's the idea. Like these things, you're gonna see that once you decompose it or you get a hierarchy, it kind of gives you some mixture of expanders and connection between them is like DAG-like. So you see precisely today.
Close enough to being a DAG.
Yeah.
Okay.
Let's start with expanded decomposition. Let's recall it in an Redis graph. What it is, you have some graph that doesn't look like expander. Let's say like this is like a clique or something, and there's some sparse cut. It's not an expander. And you have graph, you have parameter phi. What is expanded decomposition? It finds some cut edges. It cuts something. Okay. The cut size is small, like 5 fraction of the graph. And once you cut it, then the graph become expander. Then this node weighting G become expanding. Okay. So like this, like when you cut edges crossing the components, then each component here become expanding. That's what we have before. Okay. G minus C is a phi expander. Okay, let's do it in the Redis graph. It turns out that the theorem statement is going to be the same, but we need a picture to really understand what it looks like. The theorem statement looks like the same. You have a graph, phi, and you find a cut C. C should be small. And in G-C, the degree node weighting become expanding. It's just exactly the same statement, but what does it really look like to you? As human, we need intuition, not just statement. Okay. So it looks like this. It looks like something that you delete a bit, and then you get a component, like you get DAG of expanders. For example, imagine that you delete this thing. In the beginning, the whole graph is strongly connected, right? They are connected, like think of this as a clique maybe. Okay. Each of these components is a clique. And everything can reach everything in the beginning. It's just one strong component. But now imagine that you delete these edges, the blue edges. Now you get these components. And each part is expanding. Yeah.
So basically, we want to turn the original graph into a DAG of connected kind of components.
Yeah. We want to turn the graph into DAGs of connected expanders.
Okay. But does that mean that we intuitively kind of want to remove the edges which make up a cycle of them? Or?
Yeah. We kind of want to remove few edges that like make up the cycle. Like so basically try to remove few edges so that you get DAG of expanders. Yeah. Okay. Like before deleting, you might have this cut that is sparse because there are just like two edges crossing in this direction, and like the volume here are big. This is not expander, but okay. Now you delete something, and each components now are expander. Okay. So you should think like delete a few fraction of edges to get DAG of connected expanders. That is expanded decomposition. Okay. Make sense? Previously, in undirected graph, you delete 5 fraction of edges so that you get disjoint component of expanders. Here is like delete few edges, like 5 fraction, to get DAG of expanders. Okay. So, yeah, try to internalize this. Yeah. This picture should help. And you can talk about any node weighting, right? Okay. Like you have a graph, you have a node weighting phi. You want to delete like a set of edges of size phi times a, roughly, so that a is expanding after removing c. Okay. So suppose that a is here. Okay. A is like this. I might just remove one edge. So that once I remove this edge, then I now get 2 connected components, 2 strong components. This is now big component. But A here is still expanding in this component, right? Because although like there is some sparse cut here, that's like separate this component. It doesn't separate A. So this sparse cut is not sparse cut with respect to A. Okay. So this is one example of expanded decomposition with respect to A. Because A here is expanding in this component. Although the whole thing here is not expanding, A is expanding. And this component, A is expanding, like before. Okay. So you get A is phi expanding in G minus C, because on each strong component of G minus C, A is expanding. Okay. Is the statement clear? Okay. Now, how to build this thing? Do you recall like a existential proof of expanded decomposition in unrelated graph? How did we show that it exists? Okay.
Just if there's a sparse cut, remove some of the edges or remove the edges in it, and then repeat until there's no sparse cut.
Yeah. Once there is no sparse cut, it's expanding. Okay. So just keep finding sparse cut, cut it. Once it's not sparse cut, just by definition, it's expanding. And why the cut that we have found should be like small? Like the cut size should be small in total previously in another graph.
I mean, we just used like the budgeting argument where each node has a budget that's like proportional to like phi log n times the.
Yeah, that's like a kind of formal step in the proof. But I would say that like the intuition why it should be small is just because we cut along sparse cut. So we cut few things in each time. Okay. So that's the algorithm, right? As long as phi is, but now like in the related graph, it's just going to be the same algorithm actually. So as long as A is not expanding, phi is sparse cut and cut it. But now there is some direction when you say it's sparse cut. Like if it's a sparse cut, if S is out sparse, then you cut it along out cut. You want to cut only few things. So if it's out sparse, I only cut along the out edges and include it into my collection of cuts. If it's in sparse, then cut it along in edges. Okay? So if it's out sparse, then cut this guy. Like if they are like it's out sparse, then cut in this way. Otherwise, if it's in sparse, do it in the opposite direction. Once you cannot do this, then you return C. And you should try to do as an exercise that this just gives you expanded decomposition. Like once you stop, A is going to be expanding. That's clear. Why the cut size is like a phi times A times phi times log n times A. Well, it's just the same argument because we cut along the sparse cut direction. Okay. So think of this. If this doesn't, try to convince yourself. But at least it should be intuitive to you. Maybe it kind of helped to draw, actually, so that you can see this in action. Like, imagine that I have a graph. Okay. And then maybe I find a cut, and it's sparse in this direction. So like there are a lot of maybe. Okay, good. This is a graph, and there are a lot of edges here, but there are few edges here. Okay. So I cut this thing. And now I just need to recurse on both directions, on both sides. Then maybe I find this cut, maybe a lot of edges in this direction. And I cut a few things here. So now like there's like this component. And then maybe I find like this cut, a lot of edges here. This direction is small. Okay. And yeah, so you see that at the end, basically I get this component like kind of dags. Like suppose that I cannot find any cut anymore. This is like a DAG of expanders. And there are like just few things that I need to delete. Okay. So yeah. So I hope you like this animation should kind of should see that okay, it gives you a way to cut few things so that you get DAG of expanders. Right. Now let's talk about expanding balance separator in the related graph. Okay. We learned about this in unrelated graph that for any graph there exists a set F, right? Such that when the set F itself is expanding in G. The red edges here is expanding in G. And each component, after removing F, each component has size at most half. That's undirected case. How should it look like in the directed case? Just the same. You have some graph. For every directed graph, there is going to be a set F such that F is expanding. And when you remove F, each strong component has size at most half. For example, this is the graph F, the graph G. Then the set F can look like these red edges. Once you remove it, you get DAG of components. Each component should be less than half. The component might not be expanding, right? It's just some strong component. You get like a component of DAG of small components, but F itself is expanding in the whole graph. Mm-hmm. So I hope that this picture is clear. And we also saw an algorithm how to build this F, which is just keep finding sparse cut and adjust what F should be. Now the algorithm is just like this. You start with F to be everything. If F is not expanding, there is a sparse cut with respect to F. Let's say the cut is on the smaller side. Otherwise, you can flip it. You can flip to the other side. And then you adjust F. Okay. So, for example, if maybe F look like this first, okay. And then if I find some cut, and let's say it's out sparse, okay, there are a lot of in edges here. If it's out sparse, then what I do is that I'm just gonna remove everything here from F, remove it, and then I add this thing. Okay? I add this thing, and then I remove this thing. Okay. This is just how we adjust F. So the thing that we add is going to be small compared to the thing that we remove. That's how we make progress, because it's sparse. If it's in sparse, then we just do it in a similar way. Just do it in such a way that you add less than what you remove. And this new component is going to be less than half. So it's just the same algorithm really. Like really kind of natural generalization. And you should try to convince yourself that this works. The same proof. Question about this? Question about how we adjust F when we fire a cut. Are we good or not? Should I proceed? Okay. Right. Okay. And recall that like now we go to hierarchy. And so before I define it, let's try to construct it. Okay. I just want to do this as a showcase that like sometimes instead of trying to define things, like you can hope to define good notion just by constructing it. Like just see like how to build something using very natural algorithm, and whatever you get, then just write down its property. That's the notion. Like I could just say that instead of I define what is expanded decomposition, I just say that okay, I have a graph. I keep removing sparse cut like this, then I see what happened. That's expanded decomposition. Okay. And here let's do what should we, how should we define what is SC hierarchy?
I guess we could keep finding expanding balance separators and kind of recurse.
Exactly. Exactly.
We get like log n depth.
Yeah.
Every component is like at most half the vertices, right?
Exactly. Yes. So we see how to build this in a natural way, exactly like Akbar said. Just find balance separator, expanding balance separator, and recurse. That's how we did in the unrelated case. In unrelated case, we have expanding balance separator, and we just first like we can get this thing like kind of some hierarchy with log n depth. How? Just find expanding balance separator. Set this with some edge, like the top level separator, and recurse on each component. Like this, you find a separator, and for each component, you just find a separator on each component. And then you recurse on each component here. So that's just gonna give you SE hierarchy in unrelated case. There's gonna be log n recursion depth because each piece has size less than half. So now let's see what happened in the related graph. Okay. Just gonna do the same thing. Just find a top level separator, EL, to be this expanding balance separator. And then what we're going to do is to recurse on each strong component. So how should it look like? Okay. I think the important point is the picture, actually. So we might find this thing. Okay. Like I find some edge set that is expanding and it's balance separator because when I remove it, then I get to this piece. I get strong components that are separated and each piece is small. In each component, just recurse, and maybe you get something like this. Like you remove, if I remove just two edges here, then I get three components like this, that they are connected in the DAG-like way. And this green thing is expanding inside H. And recurse on each part in H prime. This is like a edge that's separate strong component into 2. Right? This. So the important thing is to note that like the edge that is expanding and it's a balance separator, like it doesn't consist of both directions. You just need to remove one direction, and there are a lot of there can be a lot of edges in another direction. Okay. So this green thing in total, you can just say that okay, on each component is expanding, so it means that EL minus 1 is expanding in G minus EL. Okay. So what you can say as a definition then is like SE hierarchy of a graph, like a phi SE hierarchy of a graph G, is a partition of edges from E0 up to EL, so that EI is expanding in G minus, like G minus EI plus 1, EI plus 2, up to EL. Yeah. So G minus E more than I. Okay. So when you like, this is the case here when EL minus 1 is expanding in G minus EL. EL minus 2, when you recurse on each component here, it's going to be expanding in G minus EL minus 1 and also when you remove EL. So this thing. So you can see that like we kind of develop our notation in a nice way that like you can see that it's just the same definition in the Reddit graph. But the mental picture that you have in mind actually is a little bit it's quite different. Okay? But the notation is quite good. Maybe the example that like to see is like this. Okay? This might be another good example. So you have that like the graph is strongly connected. So the level 3 cluster is like the green thing, the big green thing. E3 is this green edges, this green edge. So that when you remove it, then you get red components. And the green thing is expanding in the graph. And then for each red component, I have that E2 is the red edges, the red edge here. It's expanding in the red component. This one, the red edges is expanding inside. And it separate the red component into blue components. Then you have blue components, and the edges inside blue component is expanding. But you don't just have that. You have some other edges that is not really expanding. Like I mean like you can say that the black edges here is the dark edges. And you see that this dark edges is expanding in G minus E more than 0. Like when you remove all the color edges, that's a dark. And the dark is expander, just by definition, right? Like this graph looks like a DAG. This is just G0. This is exactly just E0 actually. And E0 is expander. It's a DAG, so it's expanding. Okay. I hope this picture makes sense. Okay. So So yeah, try to convince yourself that you can get 1/4 SE hierarchy with depth log n in the directed graph. This is the same algorithm, so just try to recall this, but yeah. Okay. So that's basically kind of a partition view of SE hierarchy. We have another view too. Like we have like a hierarchy view. Okay. Like a partition view is just here. Like I just define it like a partition of edge set. But for intuition, let's look at another view of SE hierarchy, which is a hierarchy view. But now, since the graph is directed, I actually need one more thing. I need vertex order. Okay. So think of this vertex order tau as if the graph is a DAG, then it's just topological order. But here it's not quite that because the graph is not a DAG. But think of some order. Okay? And we said that the edge is backward if it go in the backward way. Like I have this order, if an edge goes in this way, tau of u is more than tau of v, then this is backward. Okay. I have this is tau. Okay, so we can define hierarchy. This hierarchy is the same way. It's just a laminar family of vertices. Like before, this is the same. But think like you have tau. We have ordering 1, 2, 3, 4, 5. Okay. And hierarchy is just laminar family of these vertices. Okay. And the edge that go backward is just the edge that go backward in tau. And you can actually like think like this hierarchy is just going to be like a set of intervals actually with respect to tau. Okay. So a hierarchy looks like, it's not going to look like basically, it's not going to look like this, where like there are something in here. Okay. You can draw a hierarchy in such a way that respect tau. Like each set is just an interval in tau. And here I can define like a notion of cluster, like each cluster in the hierarchy, like each set here is a cluster. Okay. Let's say a cluster H. Now I can define what is separator of H. Like suppose that I have this cluster H. There can be a lot of forward edges. But I'm just gonna say that like the separator of H is the backward edges that cross children of H. You should think like when I remove the separator, then I get this component. This like so separator of H is the backward edges that cross the components, cross the children component. And battery is just the battery, but only backward battery. Okay. So, okay. And yeah, phi SE hierarchy is then, it consists of vertex order and hierarchy. Okay. Not just a hierarchy, it has the vertex order too. Such that the separator for each cluster is expanding. Okay. So I could just like draw all this thing in one line, really. Okay. So that you see, like I can draw like this thing, like first, then this second, this third. Like I can draw it such that each cluster is like interval in this ordering. and then like the green thing is just the backward edges that is expanding. That's separate a cluster. Okay. Anyway, this is the definition, and I hope you question about this. Is it clear or not? Yeah.
I guess I'm a little confused on like where the vertex order part is coming in, because like if we kind of forgot about the vertex order and just had like clusters such that the separator is expanding, then it seems like that still kind of achieves the goal, and maybe this like is inducing a vertex order of some sort, but it isn't like.
So like I kind of need vertex order just so that I can define separator. For example, if you look at the green thing, okay, like the green components, there are a lot of black edges crossing these components. And these black edges, there are many. They might not be expanding actually.
Right.
I only guarantee that the backward edges crossing the component is expanding. Okay. So you should think like there can be so many forward edges. And I only guarantee expansion of backward edges. Okay. Okay, so maybe let's draw something like, yeah, I hope animation will help. Like, I start with the graph, and maybe I find like some separator. And once I like it's such that like okay. So this is like a kind of H1, H2, H3. Okay. So once I find this kind of separator, then basically now I can write down my vertex order in such a way that I know that everything here is H1. I don't know the order inside H1 yet, but everything in H1 is going to be before H2 and H3. Like this, because it's like this. Once I remove the green edges, it looks like H1 come before H2, come before H3. Okay, and then inside H1, I can find like maybe some backward edges so that again like there can be a lot of edges here like this. Okay. And the red edges here is expanding in H1. The red edges is expanding in H1. So this will basically now kind of separate it into 3 parts and call it H'1, H'2, H'3. And so now like it kind of define how the order should look like inside H1. And if you recurse all the way down, you can see that it really induces vertex ordering of the whole graph. Do you see this? How you get how like this procedure like induce this vertex order tau, and also that the separator, the backward edges that separate the components is going to be expanding. Is this clear? Yeah.
So tau's should end up being like a topological order on the resulting DAG after we remove all of the non-DAG edges, or
Yeah, once you remove all the color edges, you get some DAG. Tau is going to be the topological order of that DAG. Okay. And once you remove all the color edges, basically the black edges is like E0. It's like the edges at the lowest level, which itself is an expander because it's a DAG. It's an expander in the sense that each component is expanding. Okay. Lastly, you can also justify BSE hierarchy in a similar way, like just the same, but now like the boundary is expanding too. When in the partition view, instead of EI is expanding, you can say that it's just going to be E at least I is expanding. Yeah.
So we define the boundary of a cluster also using the tau? Or?
Yeah. Boundary is just like here, backward edges, leaving H. Yeah. Okay. So we can define this thing in a natural way. I will not go over this. It's just extension of that. What I want to discuss is this. So right now, this notion, expanded decomposition and expanded hierarchy, is kind of just new, actually. Like, it's introduced not too many years ago, especially in fast algorithm. Like, this is my work that's introduced expanded decomposition to fast algorithm in directed graph. It's used to get some dynamic algorithm. And SE hierarchy, right now we find some application. One is MaxFlow in n squared time. It's much simpler than like the one that takes almost linear time. Just it's quite small number of pages, and we're gonna see that. And together with Gary and my student Ben Yu, we also use it to get something called fault-tolerant strong connectivity preserver. It's some kind of graph specifier, which I want to define, and we improve the bound from something like close to n squared to just n log n. Like really cool. So right now it's new, and it has found some application, but there should be many more. Okay. So it's exciting. Like just learn whatever you have learned in this class for undirected case. Try to look into the directed graph and try some application, try to build fast. Okay? Right now, you kind of an expert in undirected case. Like the thing that you have learned is just at the frontier, and try to make it work in the directed graph that's already like publishable. Yeah. The state of the art right now is that fast algorithm for directed expanded decomposition and hierarchy is just really under development right now. Like fast algorithm for expanded decomposition is just shown here this year. Okay. And for hierarchy, not yet. But you see like that, whatever we have learned for undirected graph, it just extends to the directed graph. And for example, SE hierarchy, we should expect that what we learned today, like in this class, we should make it fast in the directed graph too. Just try to use cut matching game and so on, right? So yeah, so an approach research direction. After this course, you can basically, for example, try to get fast algorithm for SE hierarchy or BSE hierarchy using polylog MaxFlow, or even without, the one that use only push label. Okay. And find more application. But yeah, like the next 3 class or something, we're just gonna see how to use SE hierarchy for MaxFlow. So that's the goal for the rest of the course. Questions?
I'm curious if there's anything like tree flow sparsifiers
Good. Great question. So one can prove that tree float specifier doesn't exist for the related graph. But BSE hierarchy exists. Okay. So yeah. Like you can build BSE hierarchy. It's just that once you build it, it's like this. Like you get some hierarchy that like they are connected in a DAG way. It doesn't like kind of give you a tree. It kind of give you more like a DAG actually. Yeah. Okay. All right. So yeah. So then next class I just gonna like start really talk about this thing, how to get combinatorial map flow in n square time. All right. See you next class.